In this video here, we're going to be learning how to solve systems of equation using elimination. And so elimination is the third method to use for solving systems of equations. So I want to mention that you can use any of these methods to solve for systems of equation, but they all have their advantages. And so in this case, I'll let you know what's the advantage with elimination is that it works really well when the equations are both already in standard form. And there's reasons why, and I'll explain in a moment. But the first thing to do if you want to solve something using elimination is make sure x's and y's are lined up. What that means is if you have an equation, the y's are on top of each other or lined up, and the x's are lined up. So the reason why elimination works really well for standard form is because it needs to be set up that way in order to do elimination. And then once you have that ready to go, you're going to choose one of the variables to cancel out. To do this, in order to cancel out a variable, they need to be the same coefficient but opposite signs. So what I mean by that is in order to cancel out a variable, if you happen to have like a, let's say a 5x, in order to cancel out with a positive 5x, you need a negative 5x. And that way they can cancel each other. Because 5 minus 5 is going to be 0, and so they cancel each other out. So in order to cancel out a variable, you need the same coefficient and opposite signs. So one's positive, one's negative. And also another thing about elimination is that when you're setting it up, you need to add both equations together. So I'll show you what I'm referring to with example A. I'll come back to fill out this table here, but in order to see what this table is about, let's go through the 3 example problems below, and then we'll go back and fill the table. So using elimination here, like I said before, you got to make sure the x's and y's line up. And because it's in standard form, it was already showing that the y's line up and the x's line up and the constants line up. So from here, the next step is to choose a variable to cancel out. So you can choose x's to cancel or y's. But here's the thing. When you're deciding which variable to cancel, choose the one that's easiest to cancel. Like I noticed already, the x's already are opposite signs and the same coefficient. Well, in order to cancel out a variable, they need to be same coefficient and opposite signs, and the x already does that. So I'm going to choose the x's to cancel. So when I put these two together and I add the equation, I need to grab the, so when I add these two equations, because elimination means that you have to add both equations, well, when I add the positive 2x and the negative 2x cancel because they're opposite signs and same. 3 and 5, if I add them, I get 8y. And 6 plus 10 is 16. Notice that when I get down to this, elimination allows me to cancel out one of the variables if they're the same and opposite signs, and lets me only have one variable so I can easily solve. So just divide 8 over, and y is equal to 16 divided by 8, which is 2. So now that I have y, I can choose one of these equations to use. So if I were to number this, let's call this guy 1 and this one 2. I'll just plug it into the first one. It really doesn't matter. So if I go back and plug into my first equation, which is 3y, I know what y is. It's 2, because I've solved that. And I don't know what x is, so I'm going to solve for x. So 3 times 2 is 6. Bring down the 2x. I'm going to subtract over 6. And I'm left with 2x equals 0. 0 minus 6 is 0. If I divide by 2, anything that's 0 divided into 2 is going to be 0. So in this case here, my x is 0, my y is 2. Remember, we're going to write this as a coordinate. And when you're writing as a coordinate, make sure you write x first, so 0 first, and then the 2, the y. And this is one solution because it's one set of x's and y's. So one pair of coordinates. And that's it. So that's my first one here. Let's try the next one. So for this one here, I want you to notice that the y's, or not the y's, the w's line up and the z's line up. So they're using different variables here. It's perfectly fine to use different variables. They work the same way as x's and y's. But I'm going to number my equations. I'm going to call this one 2. And what I need to look at is decide which variable that I want to cancel. And the best way to figure this out is to figure out which one's the easiest to manipulate to make them the same coefficient but opposite signs. So what I notice is that like the -6 and the 3, I can easily make both of those 6, a coefficient of 6. This guy's already 6. And this guy is just a +3. So if I multiply this here, this 3 by 2, I can make this 3 a 6. But if I multiply the 3 by 2, I have to multiply everything inside by 3. So now I just have to think about the sign. This one's already a negative sign, and this is already a positive sign. So I don't need to distribute a negative to make them cancel. So if I were to add these equations together, let's first clean this up. So I'm going to bring down the first equation, which is -6w minus 8z equals -44. The second equation, I'm going to distribute a -2 in, so that's 6w plus 12z plus, well, 2 times 36 is 72. From here, I need to try to combine or add the equation, but notice how like the w's will cancel out because they're opposite signs and they're both 6. So that cancels, leaving me with -8 plus 12 is 4z, and then -44 added with 72. They're opposite signs, so if I add them, I get 28. And it'd be a positive since the positive here is bigger. And so if I divide by 4, that cancels. Z is equal to 28 divided by 4, which is 7. All right, so I have Z. I still need to find W, so the hard part's over. All I have to do is plug in Z into one of these equations. I'm going to choose the bottom equation since it has fewer negative signs. It really doesn't matter which one you choose, but I'm just going to choose the bottom one. So I'm going to choose the second equation, plug in my 7 into Z, so I don't know what W is. So if I plug in 7 and work this out, I get plus 42, bring down the 36. If I subtract over 42 to try to get the W by itself, I get 3W equals 36 minus 42 is going to give me -6. And if I divide by 3 here, my W is going to be -6 divided by 3, which is -2. So I have my Z, I have my W, so I can write this as a coordinate. And yes, you can write this as a coordinate even though this is not X and Y's. You still can. Make sure you do it in alphabetical order though. So in this case, this is going to be -2 because W would come first before Z. Think about the alphabet. And this would be written as one solution because you have one pair. You have one X and one Z. All right. So this is my answer. Okay, so let's move on to the last two here, which are the weird ones, but let's go ahead and do them. So for C here, I have 2 equations, and I need to try to cancel out one of the variables. So X's and Y's are already lined up, so if I had to choose which variable to cancel, I can't go wrong with either of them. But maybe I want to make the 3, I noticed the 3 and 6, and 3 and 6 can both be 6. This one's a negative and this one's a negative, so I'm going to distribute with a -2, so that way I can turn this guy to be a positive, and this guy can stay as a negative here. So if I were to do that, my first equation would end up being -12x plus 6y equals -10. So I distribute the -2 to each term. I'm going to bring down the second equation. Now, I'm not doing anything to the second equation. I'm going to keep it the way it is. And so if I were to add these 2 equations, so I've already distributed the -2. If I add, I notice something strange happens. Notice how then the x's cancel because they're already opposite signs and they're both 12s. Because I distribute that negative 2, it causes it to be 12s and opposite signs. And the y's are also opposite signs in both 6s, so they cancel. So on the left-hand side of the equal sign, I just have 0 because all the terms canceled. Whereas this side here, I have a negative 10 plus a negative 10, which ends up being negative 20. So these don't equal each other. 0 and negative 20 are never equivalent. Because they're never equivalent, this here is going to be a no solutions. And that's because that means that these two lines are parallel. So if you have two lines that never intersect, or you get a weird solution where both sides are different numbers so they can't equal, this means that it's no solutions. So the last one here is D. And so if I take a look at D, X's and Y's already line up, which is great. And now I just need to decide which variables to cancel. Now, lucky for me, they're both already opposite signs, so I don't need to distribute with a negative. Maybe I'll try to make the, I noticed this is a 2 and this is a 5. 2 and 5 are smaller integers, so they're a little bit easier to multiply with. And so 2 and 5, the number they have in common is 10. So I'm going to multiply the first equation with 5, and then the second equation with 2. And if I were to do that, I need to also add. So if I distribute a 5, I get 10x, positive 10x. 5 times 8y is going to be 40y. And 5 times 6 on the far right is going to give me 30. All right, so from there, I need to distribute my 2 into the second equation, which is going to be negative 10 minus 40y equals negative 30. So if I add these two equations together, I start to notice like the first equation canceled, the second equation canceled. The second term canceled. And so the left-hand side is equal to 0. But the right-hand side is also equal to 0. 30 minus 30 is 0. So both sides are equal to 0. If both sides happen to end up being 0, they always equal each other. So this means that both of your lines had to have been the same line in order to subtract perfectly to get a 0. So if they're the same lines, that means there's infinitely many solutions. And so you can say like both of these are the same lines when you graph. And that's it for that problem there. So now that we've kind of seen quite a few problems with elimination, and you can kind of see why elimination is preferable for standard form, well, it's because it makes it a little bit easier format to add the equation when it's in standard form. It makes it easier that the x and y's are lined up to be able to cancel them nicely. So looking at the problems that we did, notice that most of the equations we got were one solution, where when you found the x and y's, those were like one solution problems. Whereas when you got something weird and goofy, like where you just got things to cancel and you got a number on one side and a number on the other side, well, you could, with those situations, you could either have a no solution or an infinitely many amount of solutions. And let's understand why. So when you get the case where you've canceled out some things and you get a number on both sides, but they're not the same numbers, then that means it's a no solution because it doesn't make any sense to have different numbers equal each other. Whereas if you got things to cancel out and both sides end up being 0, then that is a possible infinitely many solution. So for this table here, we're just showing an example for each type. So if you have one solution, that's where you have x as some number and y as some number. So you have a coordinate for that one solution. So an example that would be something like maybe problem A as 0, 2. that would count as a one solution because there's only one coordinate system. Whereas no solution would be very much like part C, where you were working it out, but then you notice as you canceled out things, both sides had different numbers, so they can't equal each other. So that's a no solution. So let me write that as an example. So if you had 0 on one side and the other side was equal to 20, well, those can't equal. So this is no solution. And last but not least, infinitely many solution. If you look at part D, that was a great example where down the line, if you started canceling things out, everything cancels, so you get just 0, 0. So for this last part here, if both sides are equal to each other and everything else canceled out, then you can say this is infinitely many solutions. Or let me draw an example of that. Like oftentimes this is an example. If you cancel everything out and one side is 0 and the other side is also 0, then that means that you have infinitely many solutions. All right, and so that's the end of this video. If you have any questions, feel free to email me. But that's it. Bye, guys.